If you look on the course webpage, you'll notice a couple of things that might be interesting. In particular, the location of the exam, which is either in 165 Everett or 119 MSEB, depending on the first letter of your last name. If you find yourself running late, go to the closest room. We've got a lot of slack in both of these. There's a brief description of what the exam will cover. And as of about 15 minutes ago, there is a handout listing a bunch of study questions, some of which may in fact show up on the exam. But you know, if the way you study is by answering all of these questions, I'm reasonably confident that you will do well. One thing I would recommend is, you know, there's a bunch of different kinds of questions here. In particular, number 8 here lists a bunch of true-false things. There will be a list of true-false questions as one of the problems on the exam with the grading scale you see at the top of the page there. For everything else, honestly, what I would recommend is pick one at random from each, and then try to answer them under as close to exam conditions as you can. And that will give you some idea where you know, there might be some places where you need to either get some help from other people in the class, get some help from us in office hours, or in the informal review session on Thursday, or get some help on Piazza. One thing that actually worked fairly well last semester and the semester before, teaching 473, is a couple of students took the initiative of creating a Google Doc, globally edited, and crowdsourcing solutions to past exams. So we don't have a lot of past exams for this class, so you can imagine this is like the union of 10 years worth of past exams, which is exactly what I have for the algorithms part. It's not a bad suggestion. It's not a bad idea. Go out and crowdsource these things. Feel free to ask about them in lab tomorrow. Feel free to ask about them in the review session on Thursday. Feel free to ask about any of them in office hours. Definitely feel free to ask about any of these in Piazza. One interesting thing that I have to be aware of when I walk into the review session, which, you know, by that point the exam will have been written. If you happen to ask me a question that is on the exam, I can't say, I don't really want to answer that. Because then you know that it's on the exam. So I have to answer it. Not surprisingly, the people who are in the room when I answer that question tend to do better on the same question in the exam. So I'm hoping that there will be more people here on Thursday than there are today. I understand why there aren't that many people here, because the stuff we're talking about in class today, it's not going to show up on the midterm on Thursday. It's only going to show up on the midterm in a month, and on the next homework. The other thing is, if for some reason you need a conflict, there is a web form that you can use to sign up that will, among other things, ask not only, who are you, but what. Well, that's not my password anymore. That's one of the bonus questions on the exam, by the way. What's my password? So, who are you? Why do you need to take conflict? When are you available on Monday? And the when are you available on Monday is so that we can schedule one time so that we don't have, we don't have to ask me or the TAs to sit in a room for 6 hours. Basically, you just want one time when everybody's going to be there. Now, if you don't mind, everybody chant along with me. Yay! Okay, new password. Okay. Waiting. Done. Good. So right. The question will be, what was my password? Please fill this out by tomorrow night so that we know how many people are going to be in the exam and we know when we can schedule it far enough in advance to actually make an announcement and plan for it. Are there any other administrative stuff? Homework 3 was due half an hour ago. Homework 4 will release after the exam. Okay, so if there are no more administrative issues, then let's go back to talking about recursion. And in particular, I want to start by talking again about Quicksort. Okay, so, oh no, go the other way. All right, so you're given an array that's initially unsorted, and you want to sort it. So the way Quicksort works is you pick out some element as the pivot, you partition the world into the stuff that's smaller than the pivot itself, and the stuff that's bigger than the pivot, and then you recursively sort the left side and the right side. Yes?
For going back to when you mentioned homework 4,
Yes.
is that supposed to be due on Tuesday?
No. We will release it. It will be due 1 week from Tuesday.
Okay.
We'll release it after the midterm, but homework will be due Tuesday, just like always.
Okay.
Yep. Okay, so the efficiency of the algorithm, how well this works, basically depends on your ability to choose a pivot well. Okay. For most simple deterministic choices of pivot, so maybe I'll choose the first element, maybe I'll choose the last element, maybe I'll choose the middle element of the array, maybe I'll choose the median of 3 heuristic is look at the first, last, and middle elements of the array and take the one that is neither the largest nor the smallest of those 3, and that should be my pivot. All of these are going to eventually lead to a worst case running time of n squared. Okay? And the reason is that for each of these, you're going to end up with a recurrence that looks, in the worst case, say for median of 3, I'm going to need linear time to actually do the partition, and then I will split the array into 2 parts, Actually, I think it's t of 1. So in the worst case, my median is actually the second smallest thing. So if my array looks like this, I pull out these 3, this is the median, and then when I partition, I end up with this mess. So I'm going to recurse on the left. That only takes me, t of 1 time at some constant. I could ignore it. And on the right, I have an array of size n minus 2. And so the time to sort that is going to be t of n minus 2. And this is going to lead me to my quadratic running time. Okay. Right, so the problem is the pivot is in the final sorted order somewhere near one of the extremes. Now, what you'd like is, things I want, world peace, a pony, and a way to pick a pivot near the middle of the final sorted array quickly. And I need to be able to do this in linear time. Right? If I had the third one of these, right? This third one would imply something like, I'm being a little bit fuzzy about what I mean by near, but I might end up with a running time that's something like this. Okay, so now this order n on the end accounts for both the time I need to find this pivot, which is somewhere in the middle half of the array. I don't exactly know where, but it's somewhere in this range, somewhere between 1/4 and 3/4 of the way through the array. And then each side is going to be at least n over 4 things in it, and at most 3 n over 4. And it turns out in recurrences like this, the worst case is going to happen when the subproblem sizes are as different as possible. Okay. Now, if I had a recurrence like this, I could solve it using recursion trees, just like I did for the merge sort recurrence. And I would get something that looks like this. Okay, so inside the box, I'm going to write the amount of time that I spend within that recursive call, not counting anything to do with recursion. So the work within that stack frame is linear. I need linear time to find the pivot element plus linear time to actually do the partition. That comes out to linear. Now in the smaller of the two subproblems, I'm going to spend n over 4 time not counting recursion. In the larger, I'm going to spend 3 n over 4 time not counting the recursion. And each of these is going to have 2 smaller subproblems. And so on, and so on, and so on. Now, this doesn't look like a nice, pretty, balanced binary tree. I mean, the leaves on the left are going to be considerably shallower than the leaves on the right because the problem sizes are going down faster. They're going down by a factor of 4 at every step. I'm going down the left spine, whereas I'm only going down by a factor, roughly 75% going down the right spine. Okay. Nevertheless, this is enough to let you solve the recurrence. Okay, so the standard thing that we do with recursion trees is once we sort of drawn the picture and we're confident that we understand the pattern, we sum things up row by row. And the thing to notice here is every row still adds up to n. This is not too surprising, right? I'm going to spend, at every level of recursion, I'm going to look at, essentially I'm going to spend constant time on each element of that subarray. So here at level 2, it's as though I've split the problem into 4 subproblems. And for each one, I'm going to be spending time proportional to the size of that problem before I recurse downwards. Okay? So normally then I would say, so T of n is n times the depth of the tree, but that really only works if the tree is completely flat at the bottom, which is not the case here. Right? So if I draw a sort of more intuitive picture of this tree, it's going to look something like this. Right. So here's 2 subproblems, and then these are going to recurse further down. And so the question is, what do you do? How do I get a reasonable bound for the total amount of work in this tree, given that every level in the tree I'm going to do a linear amount of work? Okay? And so to figure this out, I'm going to ask 2 questions. What is the depth of the shallowest leaf in the tree? And what is the depth of the deepest leaf in the tree? Okay? So I think it's easier to look at the shallowest leaf, just because the numbers are nicer. How deep is the leaf on the far left of this tree? Exactly. This depth is log base 4 of n. And how deep is the leaf on the far right side of the tree? Sorry? Close. You take the log base. The base of the log is the number you're dividing by at every step. So on the left, you're dividing by 4. On the right, you're dividing by 4/3. Okay. So what does this mean? That means that if I want to bound T of n, I have an easy upper bound and an easy lower bound. So if I want an upper bound, I could just say, okay, let's look at this part of the tree. Cut the tree off at the shallowest leaf and just pretend that's the entire tree. Now I'm throwing something away, so I'm making the total amount of work smaller. But what goes here is now n times log base 4 of n. Similarly, if I want an upper bound, I just imagine the tree goes all the way down to the deepest leaf. And I get n times log 4/3 of n. Now, the wonderful thing about big O notation, or one of the wonderful things about big O notation, is I don't care about the base of the log. Right? There's this wonderful little identity, which is one of the things that you should write on the cheat sheet, not on this exam because it's not going to matter, but on future exams. You can change the base of a log just by multiplying by a constant. So if I want to change log base 4 of n into log base 4/3 of n, I just have to multiply by log base 4/3 of 4, or divide by log base 4/3 of 4. Okay, log base 4/3 of 4 is a number. It's, I think, about 3-ish. But I don't care, because when I wear my big O goggles, I don't care about specific constants. The conclusion here is T of n is both upper and lower bound n log n. The base of the log, the specific number that I put under the G, does not matter. as long as it is in fact a number and not some other function of n. Okay? So this tree is wildly unbalanced. The leaves at the bottom are about 3 times as deep as the leaves at the top are on the left. But it doesn't matter, because up to big O's, the depth is log n. And so the quick and dirty way of saying this is, well, every time I go down a level, the problem size goes down by a constant factor. And so the depth is big O of log n. Done. Because that big O hides the difference between the leaves on the left and the leaves on the right. Okay? So any questions about solving this kind of weird, unbalanced divide and conquer recurrence? Okay? Hopefully, in some level, this is just review. Okay? So if I could choose, find a magic way of choosing a pivot element that's guaranteed to be in the middle of the array, this would give me a variant of Quicksort that is actually guaranteed to run in n log n time in the worst case. Not just sort of in practice, not just on random data, not just on nice enough data, but actually in the worst case. Big O, n log n, full stop, the end. Now, the nice thing is that one of these 3 things actually exists. Actually, 2 of these things actually exist. I own one of these things. And I'm about to give it to you. Okay, so I'm not going to give you a pony, and I have no idea how to achieve world peace. But I can tell you how to choose a pivot near the middle of the array. And in fact, I can tell you in linear time how to choose a pivot exactly in the middle of the array, which means that in fact, you're going to get n over 2 on both sides of this recurrence, and it really is just going to be the merge sort recurrence again. Okay? So this is what I want to show you next. How do you choose the middle element of the array? Okay. Now, this is called median selection. Right. Given an array from 1 to n, find, and I'll just want to be specific about what I mean. I want to find the element whose rank is let's say floor of n over 2. Okay, in case n is odd. The specific details about, do I want to round down? Do I want to round up? Do I want to worry about what happens when n is even versus when n is odd? These are surprisingly irrelevant because of the base case in the algorithm that I'm going to show you. So the base case is very simple. If n is tiny, use brute force. And by tiny, of course, I mean any number at all. That's a constant. So the running time when n falls into that case is constant. It's big O of 1. Again, I don't care what the number is. Just pick some large enough number that will avoid any sort of off by 1 errors in the base case. Of course, when you're really implementing it, probably you want to make that 4 or 5. But when you're designing the algorithm, just say, yeah, when it's small enough, just sort and pick it, or do whatever brute force thing you want. Okay, so it really isn't going to matter all that much whether I say floor or ceiling, what I do when n is even or odd, whether I think of the median of a list of an even number of things to be, statisticians like to say that if the two things closest to the middle in sorted order, A and B, and the length of your list is even, you should define the median to be A plus B over 2, not actually as one of the elements. Okay, fine. I'll find A, and then on the way I'll find B, and then I'll actually average them and spit that out. These fine details are just not going to matter because they're all going to be swallowed up in this base case. By the way, this is the base case of every recursive algorithm. If the input is small, whatever. All right. There are only two possibilities if you have a problem where the input has size less than a terabyte. One, you can solve it in constant time. Two, it's undecidable. You can't solve it at all. Does this Python program halt on all inputs? That's probably less than a terabyte. And the answer is you can't tell. Is this a syntactically correct Python program? Doesn't matter how long it is. If it fits on a hard drive, the answer is you can do it in constant time. Constant may be, I don't know, 10 years, but fine. All right. Okay. Now, the way we're going to do this is we're going to do something recursive. Okay? So I'm going to imagine here is my array, and I want to find the median somewhere. And the algorithm that I'm going to use is something called one-armed quicksort. I'm going to do exactly the same thing that I do for quicksort, except I'm not going to recurse on both sides. I'm only going to recurse on one side or the other. Okay, so I choose a pivot somehow, and then I partition. And let's suppose I end up splitting the array like this. Now I'm trying to find the median, the element that's right in the middle. Right? So if I'm lucky and the pivot ends up at the right spot in the array, then I'm done. Right? If after partitioning I have exactly the right number of elements smaller and exactly the right number of elements bigger, I don't have to do anything else. I've actually found the median element. On the other hand, it's possible that if the pivot index is less than n over 2, as it is in this picture, the pivot ended up slightly to the left, then I only have to recurse in the array on the right side of the pivot. Right, so P is the index where the pivot ends up. And finally, if the pivot index is too far on the right side, then I only need to recurse in the left side of the array. Okay? So this is the intuition. So if I want to find the median of this entire array, I pick a pivot somewhere and I partition the array. And then I ask, is the pivot actually the median? Or is the median on the left, which is going to be in this case, or is the median on the right? And in this case, the median's on the right, so I need to sort of recursively search on the right. Now, why did I put the word recurse in scare quotes? You have your hand up. That's one reason, because it may turn out that the pivot is actually the smallest element in the array. But there's a more fundamental problem. It's not just that naive recursion would be slow. It's that naive recursion would be wrong. If we recursively look for the median of this chunk of the array on the left, we're not going to pick the thing that's in the median of the original array. We're going to find something sitting here. Right? Its rank is going to be too high. And so we're not actually going to find the thing that we're looking for. Yes? We're looking for the element that would be exactly in the middle of the array if we sorted it. Okay? That's what the median means. Half of the elements are smaller, half of the elements are bigger. Okay? So if I say find the median of this subarray on the right, it's going to find the thing that's right in the middle of the subarray on the right, which is also going to be bigger than all these things on the left, so it's not going to be in the middle of the original array. Okay? So if I actually want to phrase this as a recurrence, I have to solve a slightly more general problem. I can't just say, to find the median, I partition and then recursively find the median. I'm recursively looking for something else. Okay? And so, in fact, the problem that I'm really going to solve is just called selection. Okay? So the input is an unsorted array, A from 1 to n, and an integer, k, which is somewhere between 1 and n, and the output is the kth smallest number in A. Okay? Now, median selection is the special case where k is n over 2. Right? And now, if I keep this more general problem in mind, then you can imagine that when you're recursing, right? So you're given, here's some target index k. When I recurse on one side, I'm going to keep the same k, and when I recurse on the other side, I'm going to say, well, I also have to keep into account these p things. So I need to reduce the index I'm looking for. So let me just show you the pseudocode. Of course, I used R here instead of P for the output rank of the partition element. But here is Quickselect, or one-arm Quicksort, as it's almost universally known. And in this case, rather than choosing Googleplex as my base case, it turns out the algorithm is correct, even if I bottom out at n equals 1. Okay. So somehow I'm going to choose a pivot element. Again, this is sort of the magic part of the array. Now, at this point, you may be thinking, the whole point of doing this selection is that so I can choose a pivot element for Quicksort. And now I'm giving an algorithm that looks kind of like Quicksort. Maybe that choose a pivot thing is going to be recursive also. Yes, it will, but not just yet. Okay? For now, let's just imagine the pivot element is whatever you want, or whatever somebody wants. Doesn't matter, it's something. So I partition the array, and the partition subroutine returns the rank after I partition. It returns where the pivot element should go in sorted order. Right? So if it ends up at R, what that means is that there are exactly R minus 1 things smaller than the pivot itself, and n minus R things larger than the pivot. And now there are 3 possible outcomes. Either the rank that I'm looking for, the element that I'm looking for, is smaller than the pivot, so it's on the left, and then I recurse on the left for the same rank, to the same position, k. Or the size of the element I'm looking for is it's bigger than the pivot. This is k is greater than R. In which case I'm going to recurse on the right, but when I recurse I'm going to say, you know what, I already know that this is bigger than R things, so my target rank isn't going to be k. It's going to be k minus those R things that I'm ignoring. Yes?
Is the element in the array ordered?
The elements of the array initially are not ordered from small to large. If the array were sorted, the algorithm would have one line, return A sub k. The initial array is not sorted. What you want is to have an algorithm that returns exactly the same result as this two-line algorithm. But I don't want to sort the array. Okay? So initially, the array is completely unsorted. Otherwise, the problem is one line, one instruction. Okay? Now, as someone pointed out, if I'm unlucky in how I choose my pivot, this is going to lead to, a slow algorithm. But at least with this recursive formulation, the algorithm is correct. It will, in fact, find the kth smallest thing in the original array, and it's not terribly difficult, although it's a little bit tedious, to actually prove that by induction, where you have three inductive cases and a base case, assuming that the partition algorithm works. Okay? Now, let's suppose that, I have this algorithm that just picks something near the pivot. In general, when I say near the pivot, again, suppose I could always somehow magically, in the first line of one-armed quicksort, choose something that's in the middle of the array, right? Then no matter which side of the array I recurse on, I'm only going to recurse on one side or the other, if somehow I have magic, I'm going to end up a running time that looks like this. I need linear time to partition, and if somehow magically I can guarantee that that initial pivot is in the middle half of the array, then the subproblem I'm recursing on has size 3n/4. All right, so now my recursion tree looks like this, just a chain. And now we're in the one of the other cases of the recursion tree technique. Namely that if I sum up level by level, I have n at level 0, 3n/4 at level 1, 9n/16 at level 2. In general, I'm going to have 3/4 to the I times n at level I. The important thing to notice here is this is a descending geometric series, which means the only thing that matters is what's at the root. Okay? Now, in fact, I don't need to worry about the depth of recursion here. And I could just imagine that this recurses forever. But because the problem, the problem sizes are shrinking fast, I can get, as a sort of conservative upper bound, let's just assume the induction goes on forever. Then each level I is contributing 3/4 to the I times n, and this turns out to be n times 1/1 minus 3/4, which is 4n. Okay? In actual fact, it doesn't recurse forever. At some point, the problem size is less than a googol, but fine, it's going to be 4n minus something, but the important thing is that it's big O of n. Okay? As long as I can get rid of a constant factor before I recurse, I'm going to get this nice descending geometric series, and then everything is going to be swallowed up by the root. Okay, so far we've seen two cases of the recursion tree technique. One, every level is the same. Two, the level sums get smaller by constant factor. You have a descending geometric series. Later we'll see something that's the third case where it goes up. It's an ascending geometric series, and then all the action's going to happen at the leaves. We'll get there, but not just yet. Okay. The problem is we don't quite have this magic yet. I know I promised it, but we haven't quite gotten there yet. And it's not clear that the way that I want to choose the pivot is to recurse, because if I did, then I'd have this, well, I recurse, oh wait, I'm going to get into an infinite loop. I don't want to do that. I need to somehow filter, reduce the problem size or something to choose a pivot that's actually going to work well, right? So here is what I'm actually going to do. And this is a strategy that was first described in the early 70s by my great-great-great-grand advisor and four of his colleagues when they were all either students or faculty at Stanford in the 70s. What I want you to imagine, because this is not actually going to happen by moving data around, I want you to imagine that instead of an array that's, a one-dimensional array of n things, they actually have a two-dimensional array. Right? This is just a matter of, two-dimensional arrays are represented in most modern languages as one-dimensional arrays with some indexing semantics. Just imagine that's what's happening. Okay? So in particular, I'm going to imagine that the array is made up of 5 rows, each with n over 5 elements in it. Now, at the end, I'll talk about where this number 5 comes from. It falls out of the recurrence, but for now, just trust me for a second. The 5 is the smallest number that works. Okay? Now, let's start by finding the median of each column. So how long does it take to find the median of 5 things? Constant. Good. How long does it take to find the median of 10 billion things? Constant. Good. Right? Now, I'm going to imagine, because this is not actually what the algorithm does, but I'm going to imagine, for purposes of developing intuition, that I reshuffle these 5 element columns to put the median in the middle row. Okay? Again, the algorithm does not actually do this, but this picture is just for intuition. Okay? So the total time to find the median of all n over 5 columns is going to be n over 5 times a constant. Okay, that's about n. Okay? 2. Find the median of these n over 5 medians. Right? Now, this is going to take me t of n over 5 time. I'm going to, of course, refer to the median of medians as mom. Right? Now, this is done by the recursion fairy. Right? Don't try to open the box. You will make your head explode. This is done by the recursion fairy. It is magic. The median fairy tells me the median of that middle row. And again, just for the sake of intuition, this is not what the algorithm does, let me imagine that not only does the median fairy put the median right here in the center of the array, but in fact, I'm going to reorder the columns so that the medians are in sorted order from left to right. Again, the algorithm does not do this, but I'm reordering things for purposes of analysis. Okay? Now, why do I want to do that? The reason is now, if I imagine that the middle row is in sorted order, and each column is in sorted order, everything in this upper left quadrant is smaller than the median of medians. And everything in this lower right quadrant is larger than the median of medians. Okay? So the nice feature of this particular element in the array is that it's somewhere in the middle. If you imagine, again, just for purposes of doing the analysis, if I imagine sorting the original one-dimensional array, there's 3n over 10 elements that are all smaller than mom. And there are 3n over 10 elements that are all bigger than mom. Does everybody see where I got 3n over 10? I chose half of 3 rows. Each row has n over 5 things. So half of one row is n over 10. Do that 3 times. There's 3n over 10 things in the upper left chunk, and 3n over 10 in the lower left chunk. Okay? Mom is somewhere in the middle of that range. Okay? Which means that now I'm going to do one-armed quicksort where the pivot is mom. And this is going to take me linear time to do the partition. And when I recurse, I know I'm either going to throw away everything smaller than the pivot, or I'm going to throw away everything bigger than the pivot. Either way, I know I'm going to throw away 30% of the array at least. So this part of the algorithm is going to take at most 7n over 10. But the subproblem that I'm going to recurse on will have at most 70% of the original array. Okay. Now, again, step 2, where I find the median of those n over 5 medians, that's recursion. One-armed quicksort, where I do the partition and then I do selection in one side or the other, that's recursion. The first step, when I'm finding the median of each of those columns of size 5, that's not recursion, that's brute force. Right? This is, I think, one of the sort of canonical example where if you try to imagine what's going on when you make these recursive calls, you will just find yourself horribly confused. The only way to convince yourself that this algorithm is working is to actually believe in the recursion fairy. To actually believe that, yes, in fact, if I could find the median of medians, okay, let's pretend it takes that much time. And if one-armed quicksort actually works, and okay, the recursive call takes that much time, okay, yes, then under those circumstances, I believe the algorithm works. But under those circumstances is a synonym in this case for by the inductive hypothesis. Okay, by the recursion fairy. Right? Is everyone confused about how the algorithm works? No? Is anyone confused about how the algorithm works? Now I'm going to play a trick that one of my undergrad instructors played on me when I was a student. Are there any questions?
So you're saying that you're taking the top linear array and dividing them up into 5 pieces each and then putting it.
That is how I want to think about it.
Okay.
What I'm actually going to do is, let's look at the code here. Okay. The part where I split it into 5 by n over 5, what I'm really going to do is I'm going to just look at every consecutive chunk of 5 things in the input array, pick out the median, and put it in a different array. That's the array that I had, that I thought of as the middle row. And then I'm going to select the median of that array of medians. And then I'm going to use that value as my partition element for one-armed quicksort. All right, so this is recursion 1. This is recursion 2. Right? But in order to see the analysis, in order to pull out the analysis, I'm going to imagine that after the algorithm is done, after the smoke is cleared, I'm going to say, all right, I want to figure out how much time it took. Let me imagine just, by divine intervention, I'm going to move the data around to make it more convenient for me to figure out how long the algorithm took. Right? The way that I'm going to do that is I'm going to imagine that instead of just picking out the median of every column, I actually sort the columns from top down. And I'm going to imagine that in step 2, when I find the median of medians, I'm actually going to sort the columns using their median as the key value in increasing order from left to right. I don't have to pay for the sorting because the algorithm isn't actually doing it. Okay? All right, so I'm going to do this one more time. Somebody asked me another question. Yes?
Can you show that pseudocode?
Sure. Okay. Did you have a specific question about it, or did you just want to see it? Why 5? All right. So to answer that question, I need to solve the recurrence. Okay? All right. So I'm actually quite happy that I don't get to play the uncomfortable mind game where I say, are there any questions? And I just stand here until someone asks me a question. It gets really uncomfortable after about 15 seconds. Okay, so if I put all these pieces together, I'm going to get a recurrence that looks like this. There's a linear time component, and then there's the t of n over 5 term from sorting the median or finding the median of medians, and then there's the t of 7n over 10 term because I'm doing one-arm quicksort. Okay, so I'm going to build a recursion tree. At the top level, I'm doing a linear amount of work. At the next level, on one child, I'm doing n over 5. On the other child, I have 7n over 10. Then I have grandchildren. Over here, I'm going to do n over 5 over 5, 25. Here, I'm going to do 7 times n over 5 over 10. So here, 49n over 100, and so on. All right, so I have another one of these unbalanced recursion trees, where the problem sizes are not the same at every level. But now let's watch what happens when we add up across the levels. So at level 0, of course, we still have n. We do a linear amount of work at the root before we recurse. At level 1, the total amount of work is 9/10 n. And this is a pattern that repeats, that at every node in the tree, the value at that node, the total value of the children of that node is 9/10 of the value of their parent. Which means that if I look at row level 2, I'm going to get 81 over 100n. And in general, at level I, I'm going to get 9/10 to the I times n. So now I need to sum all these values up. What am I going to get? Something times n. This is a descending geometric series, so the only term that matters is the one at the root. Now, if you're a little bit more careful with the constants, it comes out to be about 10n. Right? And if you're really more careful about the constants, you'll remember that the constant inside this big O isn't actually 1. It's something else. And so if you actually work out all the details, it comes out to about 20, somewhere between 20n and 25n. Okay? Which means, in practice, you don't want to do this. All right? But in theory, it gives you a linear time algorithm to pick out any element of whatever rank you want. Oh, come on. There we go. In linear time. All right, so the left branch of this recursion tree is finding the median of medians. The right branches of the recursion tree represent the action of one-armed quicksort. Okay, so you end up with order n. Now, there's a reasonable question that you might ask, why 5? In fact, somebody did ask. 1 is clearly not going to work. And to keep things simple, it's probably easier to imagine that we split it up into odd things instead of even, so that the two subproblem sizes, the two chunks that we're throwing away, have exactly the same size. So the natural thing to ask is, what happens if I put a 3 here? Why not split it into 3 rows of n over 3 each? Well, then let's look at the running times we would actually get then. Finding the median of medians, so finding the median of each column of size 3, that's still going to take me linear time. Finding the median of medians, instead of t of n over 5, I'm going to get t of n over 3. Then the amount that I'm actually throwing away isn't going to be 3n over 10, it's going to be 2n over 6, which is n over 3. Which means when I recurse, I'm going to get 2n over a problem of size guaranteed to be less than or equal to 2n over 3. And so I'm going to end up with a recurrence that looks like this. Anyone want to guess what the solution for that recurrence is going to be? And log n. Because at the top level, I'm going to do a linear amount of work. And at the next level, I'm going to do n work. And at the next level, I'm going to do n work. I'm going to do n work at every level, and they're log n levels. Right? So if I tried to do this median of median trick with 3 instead of 5, I would actually end up just with a sorting algorithm. Right? And the whole point is to try to find that median element without sorting. Right? Now, if I plug in 7, it works. If I plug in 9, it works. If I plug in fact, any odd number bigger than 3, it will work. Right? And even if you're very, very careful, you can make it work with 4 or any larger even number. But then the analysis is nastier because the things are unbalanced. Okay? So that is how, in theory, one actually makes Quicksort run in n log n time. All right? I run this median selection algorithm that runs in linear time to choose the median element of the array, and I use that as my pivot for Quicksort. As I said, and as you might guess from looking at the recurrences, the constant factors here are horrible. In practice, what you want to do is choose a random element in the array to be the pivot. Half the time, it will be in the middle half of the array, and that's good enough. Okay? In practice, just literally roll an n-sided die and pick that element as the pivot. Don't try to be clever. Just literally be random. Okay? There's still some very small probability that things will go bad, but as I said, there's also a very small probability that your computer will explode. It's not enough to worry about. Okay, any other questions about finding medians, selecting the kth smallest thing, this kind of recursion tree technique. Okay. I'm going to show you one more example. It's going to be a fairly brief example because of time. I'm going to let you look at the notes for the technical details, but it's a problem that you all hopefully know well. And it's a problem that actually we talked about at the very beginning of the semester, namely multiplication. Okay? So what I have here on the screen is the output of the standard lattice multiplication algorithm that everyone in the US and at least in Western Europe learns in elementary school. My third grader is not quite up to the point of learning this, but will probably within a year. This algorithm can be formalized to be a pair of nested for loops that loop, over all indices in the first number, all digits in the first number, and then for all digits in the second number, multiply them together, and then add them all up with the appropriate number of zeros at the end. Okay? So this gives you a way of multiplying two n-digit numbers in n squared time. And when you do it on paper, it uses n squared space. And it's a fairly natural question whether this is the best you can do, especially given that there's an equivalent algorithm which is often called the Russian peasant algorithm that was taught in the Soviet Union, that also runs in n squared time. There were some rather famous Russian mathematicians who conjectured that n squared is in fact the best you could do. One of them, Kolmogorov, actually set up a seminar. It's like we're going to have a special topics class where we're going to look at we're going to try to investigate this question. We're going to try to come up with an n squared proof. And one of his students, I think about 3 weeks into the seminar, came and showed Kolmogorov a faster algorithm. At which point, Kolmogorov reportedly, threw his paper in the air and said, "Okay, fine, seminar's canceled. We're done." So Karatsuba, who was the guy who came up with this, he started with the idea of, if I want to multiply two n-digit numbers together, I can think of these n-digit numbers as arrays, right? And there are lots of problems with arrays where it might actually be useful to split the arrays into smaller pieces. One of these days, this might work. Okay. So maybe it's possible to phrase multiplying two n-digit numbers, reduce it down to multiplying some n over 2-digit numbers. Right? So you can imagine, writing if I set m to be n over 2, I can write any n-digit number as 10 to the ma plus b, where a and b are m-digit numbers. And I can write the other one is 10 to the mc plus d, where c and d are n-digit numbers. And now, by expanding this out, that should be AD plus BC, sorry. By expanding that out, you'll notice that I've reduced the problem of multiplying two n-digit numbers to 4 instances of multiplying two n over 2-digit numbers. And basically I'm doing this by just sort of rearranging stuff in memory, giving things different names. And if I do this, then the time to multiply two n-digit numbers is, I don't know, linear time to move the stuff around. And then I have 4 subproblems, each of size n over 2. And so you solve this recurrence using the recursion tree method, and it comes out to be n squared. Which in fact is not too surprising. I'm looking at, you know, left side, right side, right side, right side, right side, left side. Within every subproblem, by the inductive hypothesis, I'm going to multiply every digit on one number with every digit in the other. So in fact, I'm really just reorganizing the standard lattice multiplication algorithm. I'm not really doing anything interesting at all, right? But then Karatsuba said, hey, you know, I can speed this up a little bit using the fact that I actually don't care about the individual products A, D, and B, C. I only care about their sum. And I've got some other stuff that can maybe help me figure that sum out. And so he used the following lovely little algebraic identity. I'll let you verify yourself that this equation is correct for any values of A, B, C, and D. But notice what it actually means. I can compute this middle term in this 4x4, this 2x2 recursive formulation, not by doing 2 separate multiplications, but in fact only doing 1 additional multiplication on top of the 2 that I already have to do for the bottom and the top term. So I'm already going to compute AC, and I'm already going to compute BD. With 1 more multiplication, I have enough information to fill out this middle term. Okay? And so this leads me to Karatsuba's algorithm. Here it's written in base 10, although normally you'd actually do it in base 2. You take, you know, if your numbers are small enough, just do it. Otherwise, you split your numbers into A, B for, you know, split X into A and B, split Y into C and D. And then I do 3 recursive calls to fast multiply to get the various terms that I need to glue together in the last line to get my answer. Okay. And the running time of this algorithm is now governed by this recurrence. It's not 4 calls to a subroutine with the input sizes n over 2, it's only 3. Now there's some additional non-recursive time involved in doing the additions and subtractions to get everything to work out, but that's all together going to take me only linear time. There's like 5 additions and 3 subtractions in there. Each one of those is going to be another linear time operation, but there are only 5 of them, so it's all linear. Okay. And so now let me show you how you would actually solve that recurrence, and then I'll let you go home. Okay. So again, the recurrence, ignoring floors and ceilings because they don't matter, is T of n is 3 T of n over 2 plus order n. Okay. So at the top, I have a linear amount of work from this n. Then I have 3 subproblems, each of size n over 2. And then 9 sub-subproblems, each with size n over 4. If I add up row by row, you'll notice every row is 3 halves, is 50% bigger than the row above it. I have an ascending geometric series. So in this instance, all the work is actually going to be done down at the bottom of the tree. Right? Down at the leaves, this is the only term that actually matters. Now, the value that's actually in one of those leaves is a constant. That's why it's a leaf. When the problem size gets to be small enough, I could just say, okay, brute force. And there's some constant value there. So I can imagine that the actual value stored in each leaf of this recursion tree is a 1. And then the only question is going to be how many leaves. Well, the number of nodes at any particular level is going to be 3 to that level number. So the number of leaves is 3 to the power depth of the tree. What's the depth of the tree? Now, here it actually matters what the base of the log is, because it's not just floating at the bottom. It's actually up in an exponent. So let's be clear. What exactly is the depth of the tree? It's log base 2 of n. And the reason is every time I go down, the problem size goes down by a factor of 2. Right? Now, a to the log of b is the same as b to the log of a. This is one of these things that you just know because you had high school. And this is about n to the 1.6. So log base 2 of 3 is about 1.6 something. So this, in fact, really is a subquadratic algorithm. Now, you could reasonably ask, just as you did or as you were thinking, for Quicksort, do I really want to do this? Do I really want to spend this weird recursive algorithm to actually make this work? In this particular case, there is some penalty in the constant factor, but it's reasonably small. Nevertheless, the gain here only really makes sense if n is somewhere in the hundreds or thousands. Right? If your numbers are not terribly large, just do the quadratic thing. That'll actually be better. But if you're dealing with numbers that have hundreds of digits, for example, if you were doing any cryptography at all, then in fact Karatsuba's algorithm is faster in practice. And if you look in Python, in the big integer, arbitrary precision integer library, Karatsuba multiplication is in there with a trigger of, if the number has more than a few hundred bits, use Karatsuba's algorithm. When the numbers are smaller than a few hundred bits, fall back to the standard nested for loops. Now, it turns out that this is not the best you can do. Why 3? Because that was the first thing he thought of. Yeah?
Why do we go back to nested for loops when it's small?
Because it's faster.
Why is it faster?
It's a trade-off between the function inside the big O and the constant outside the big O. Right? If the constant is 5-ish, then you're asked, the trade-off is, when is 5 bigger than n to the 0.4? Right? And there's some actual value of n for which that's true. Right? The same is true, by the way, for Quicksort. At some point, when n is less than about 20, you should just give up and use insertion sort or selection sort. There are even faster algorithms that use even more complicated divide and conquer things, the fastest of which were invented by Gauss, which we now know as the fast Fourier transform. That's all I'm going to say about that, because we're 15 seconds over. Yes, last question.
Quick question. Do you mind talking about the exam?
I'm going to say quite a bit more about the exam on Thursday.
Okay.
Do you have a specific question?
The exam is on Thursday.
The exam is on Thursday in the evening. I will be here in the room at 12:30 on Thursday.
Okay.
There's also a bunch of stuff posted on the course webpage.
Which lectures are covered?
Everything is posted on the course webpage.
Okay.
Yeah. There's a list of about 150 practice problems.